A simple approach to classification is using what's called a naive Bayes model. Actually, it's a family of models. It's a model that uses the so-called naive Bayes assumption. And let me point out here first, even though it has the word Bayes in it, it's not necessarily a Bayesian method. So if you've heard about Bayesian methods, this is not necessarily a Bayesian method, but you can do Bayesian naive Bayes. So the nice thing about naive Bayes is that it's simple and it can work. It can work okay. It can work. I mean, it depends on the problem. Not as good as there are other methods which are much better performance. But the nice thing about naive Bayes is it's very simple to understand, easy to implement, and it's a good way to describe, or it's a good introduction to generative classification models, and it illustrates a lot of the interesting methods associated with this type of model. So what is naive Bayes? Well, here's the setup. It's a classification problem, so it's a supervised learning problem, and so we're given some data, some pairs of x's and y's, x1, y1, up to xn, yn. Actually, so I'm going to use a little different notation here. Instead of putting subscripts for the points, I'm going to use superscripts, and you'll see why I'm doing that in a minute, just to keep things unambiguous. So here, each of these xi's is a point in Rd, so it's the first coordinate I will write this way. The superscript will always be in parentheses, and that'll tell you which point it is. The subscript tells you which coordinate. So this is a point in Rd, d-dimensional real space. And the y's, so I'll just say that here. So xi is a point in Rd, and I'm writing it all out in this way. And yi is oh no, it's not a real number. So yi is in some finite set. We're doing classification. This is the classification method. And y is just some, so here y, this capital script y is some finite set. Let's say maybe just the integers from 1 to m, just some finite set. So that's what we're given. And we will assume, under the naive Bayes approach, we assume a probabilistic model in the following way. So we assume a family has some set of distributions, a family of distributions parameterized by some parameter theta, could be a vector, just some parameter here. And these distributions will have the following property. This is the key property. So each of these is a distribution. It's a joint distribution. So this is a naive Bayes is a generative model. So in contrast to a discriminative model, we're going to assume a joint distribution on x and y. So here, this x is going to be one of these x's, so it's a point in Rd, and y is a point in it's a class. And the joint probability of these under the parameter theta, well, of course we can always factor it as the probability of x given y times the probability of y. We can always do that. But here is the key assumption. This is the key assumption in the naive Bayes model. Here it comes. So we assume that this part here factors as the product of the probability of the first coordinate given y times the probability of the second coordinate given y and so on up to the probability of the d coordinate given y. So this is the key assumption here. Okay, and so if we have some random variables, let's say, so we assume this family of distributions, and now we're going to model our data. So we'll let x superscript 1, let's see, how do I want to say this? Yeah, let's say it this way. y1, so we have these pairs up to xn, yn. We assume that these are distributed according to this joint distribution, p theta, and their iid, for some, so we assume that there's some theta for which these random variables are randomly distributed, and then we're going to assume that our data comes from such random variables. So this assumption here, the assumption of that the probability of x given y factors in this way. This is the same as saying that so if x, let me put that in a different color. Oh no, we'll keep the same color. So this assumption says that if xy is distributed according to p theta, then the coordinates x1 up to xd of this random x are independent given y. So sometimes we say conditionally independent to emphasize that they're independent given y. So this assumption is a conditional independence assumption. So that's the naive part of the model. So this conditional independence assumption is the naive part. That's what makes it, so-called naive. I mean, it's a reasonable assumption. There's nothing wrong with this assumption. It's just some probabilistic model. But this is what people call it, for better or for worse. A better name might be a independent feature model. That might be a better name. Independent feature model. So these different coordinates x1 through xd can be thought of as, or could be just referred to as features, the features of this x. Okay, so that's our assumption. That's the model that we assume. And now, how are we going to use this model? Well, we need to do classification with this. That's what we're trying to do, is trying to do classification. So our goal is, for a new x, we get some new x in RD, classify, or I'll say predict its y. So we want to predict the class for that x. And under this model, how will we do that? Well, we will do the following. So the algorithm that we will use is, first, this is the standard thing to do. First, we estimate theta. So our assumption here, we assume that there's this family and that our data comes from some random variables that are distributed according to that model for some theta, but we don't know the true theta. So this is the classic estimation type of problem. We have some data. We want to estimate the parameter for that data. So this, we know sort of how to do, we've seen ways how to do this. You could use maximum likelihood. You could use map. You could use the maximum a posteriori. So this is something that we know how to do. So we're going to estimate theta from the data D. And then we will compute. So we want to compute y hat, our prediction. We want to maximize the probability. So we want to choose a prediction that maximizes over all possible classes the probability of that class given this new x here under our estimated theta. So maybe I should put like theta hat here to emphasize that that this is using the estimate that we made in the first step. So we want to compute this. And that's, well, okay, so that, I mean, we could stop right there, and that would be, this would fully define the naive Bayes procedure. You compute this thing. This is the defined quantity under this model, and that's it. That's the naive Bayes. That's the naive Bayes classifier. I'd like to go a little bit further here and expand this expression a little bit so that you see exactly how this model that we've assumed, how it allows you to compute this. It's illuminating. So this thing, we'll just continue this line here. This, we'll keep the argmax over y. So let's use Bayes' rule. Remember that Bayes' rule tells us this is the probability of x given y times probability of y divided by the probability of x. That's just Bayes' rule. And now note that the denominator here does not depend on y. And since we're maximizing over y, it's the same thing. We could just forget about the denominator here and just maximize this thing. So that's, in other words, I'm saying that this, as a function of y, is proportional to this part, and therefore we have this equality. The argmax of this, or an argmax of this, is an argmax of this. So I guess technically I should put, we want a y hat that's one of the maximizers. It's not necessarily, since there's not necessarily a unique maximizer. So yeah, to be precise, I should have put this, and this is considering the argmax to be the set of maximizers. Okay, so we did this little thing here, and now, right, our assumption is that this part, our model, where's our model? Here's our model. Our model says that this thing this part factors in this way. So we can do that. Let's plug that in. Argmax over y, x1 given y. So it's the probability of each of the coordinates given y times the probability of y. And this part, this step here where I used Bayes' rule, this is the Bayes part of the algorithm. So it's not, Bayesian in the sense that we're putting a prior on parameters and integrating out that parameter. But this is why they call it naive Bayes in particular. So we can compute this thing, we expand it out, and we use our estimated theta to compute these, and we can maximize it, and we get our prediction. And so that is the naive Bayes classifier.